Great. This will be a bit redundant. I think I did the wrong button. Sorry. Sorry, no. Okay, so. Great. So we've just had a great presentation on photonic quantum computing and one of its application on VQE. But I want to delve a bit more into photonic once again. So you already have the basics. So some parts will be the same as the presentation before, but don't worry, there will still be a whole different parts, notably on the CNOTs and on polarization. So here I am giving an introduction. Here are the outlines of this presentation. So first, that's the alarm. Should I wait or should I continue? I don't know. Yes. I'll just go on then. So first, I'll describe. Okay. Okay, great. I'll continue now that everyone's awake. Sorry? Oh, okay. So first, I'll introduce a photonic model of quantum computation. As we've seen one before, but I'll introduce another. And then I will show you how to rebuild the quantum gates, the standard quantum gates, like the H gates and Pauli gates, from this photonic model using optical components. And then I will compare qubit circuits with photonic circuits. And I will show you three implementations of the CNOT gates and challenges. And I will also introduce polarization encoding onto photonic quantum computations. So there's a whole ecosystem of photonic hardware. And just as any other constructor, they are interesting to get into because we don't know which technology will prevail in the future or if a technology will prevail. So we will get into this one particularly. So there are programming libraries and different constructors. Here are some examples. Now I am going to introduce spatial mode, Fock states, and qubits. So you've already been introduced, but just in case you didn't understand, I'll repeat that part. So spatial modes are different locations in space, because it's spatial modes, on which can lie some photons. So there can be many photons in a mode, or there can be none. And it can correspond, for instance, to an optical fiber. So a Fock state is simply a description of m given mode of how many photons are in those given modes. So I use this notation. you didn't have the little index at the bottom before, but I use that to differentiate normal qubit states to Fock states. It's to differentiate the notations, which can be quite confusing because you must not get confused between the ket0 state and the ket0 with index 0 state, which is a Fock state and not a qubit state. So we have two examples of Fock states with 4 photons on 4 modes. We can have 1 photon on each of the modes, or we can have many in some modes and none in others. And what I'm claiming is that spatial modes can be used to encode logical qubits, as in qubits that are made of photons and not as in logical error-corrected qubits. So we have to make that distinction. So from optical components, from even macroscopic size optical components, you can build sort of a quantum computer. And the most used components are beam splitters, which are semi-reflecting mirrors, which means when you shoot a beam onto one of those mirrors, then half of the beam's wave function will be reflected, and half of the beam will be transmitted through the semi-reflecting mirror. And I want to put an emphasis onto one sentence from Hertel on his paper introducing a library for photonic quantum computation, and it is that photons have many degrees of freedom and offer a rich variety of ways to encode qubits. So we saw in a previous presentation an encoding by Orca Computing, and one other, which is the most common approach, is the dual rail or dual path encoding. So I want first to, before introducing the qubits, and I want to introduce really the physical optical components which are used. They have already been presented, but I'll do a reminder. So first there's the phase shifter, which is a component such as a lens, which will just be on the path of a photon, which will make it go slower than its one which is not slowed, and this introduces a phase difference between the rest of the system. So if you have 2 modes in parallel and you apply a phase shifter onto one, then if a photon was there, it will slow the photon down and input a phase onto its Fock state. Then there is the beam splitter, and it has a unitary action onto Fock states, and there's the matrix of the application of a beam splitter. And this matrix looks a lot like H, because if you input pi over 2, then you get instantly the H matrix. But be aware that this acts onto Fock states and not the qubit states. But we will see that there's still a correspondence, a connection between the two. So here are 2 representations of, on the left, a phase shifter, and on the right, a beam splitter. And one last component, which is not really a physical component, but it's a component that we will use into photonic circuits. It's the permutation component. It's simply acts like swapping the spatial mode, and so it swaps the number of photons on each spatial mode. For instance, the permutation component associated to the permutation 1, 0 swaps the number of photons in each spatial mode. So you had n0 photon on mode 0 and n1 photon on mode 1. And then after the component, you will get N1 photons on mode 0 and N0 photons on mode 1. So here's a representation. I want to highlight the difference between qubit and photonic circuits. These are not to be confused from one to another. Qubit circuits have well, you're mostly used to qubit circuits, and I will not present the usual qubit gates. While on photonic circuits, you have different modes, spatial modes, in this case, and you apply phase shifters and beam splitters onto this circuit. The encoding I want to introduce you to is the dual-Rayleigh encoding, and it's becoming quite old, from Chuang and Yamamoto in 1995. And to encode one logical qubit, once again, not as in error corrected, but as in built from something else. To encode one logical qubit, you need two spatial modes, and it will be the qubit will be encoded on where a photon lies on these spatial modes. So you have a Fock state, and on these two modes, you will need only one photon, because if you have more than one photon, then it does not represent a qubit state in this encoding. So this is really one sort of encoding, and if you have, for instance, a photon on mode 0, then it represents ket 0, and if you have a photon on mode 1, then it represents ket 1. But having no photons at all does not represent any qubit valid state. That's why it was said before that photons have a higher encoding space than qubits, because you can have qubits on them, and you can also have other weird things, at least in this encoding. So I want to make a small comparison between the two. The state space of qubits, of standard qubits, is a Hilbert space, and you have gates, and the lines represent qubits on the circuits. And in photonic quantum computing, you have a Fock space, and you have beam splitters and phase shifters with optical modes as represented on wires. I want now to head on to how to implement in this encoding the classical quantum gates, which are the Pauli gates and also the C0. So the first one in the dual-Rayleigh encoding is an X gate. It's really easy to do, because as we can take a generic qubit state at the top, which we call psi, and we've got alpha ket 0 and beta ket 1, and we just translate the qubit state into Fock state, and we see that if we apply a permutation onto this superposition state, then we just have to swap the photon numbers in both components of the sum, and we instantly get the reversed qubit state where you have the result of a Pauli X gate, because you swap the probability amplitude of ket 0 and ket 1. So that was quite easy. Another super easy gate to implement in the dual-Rayleigh encoding is the Z gate. You want to apply it using a phase shifter. So if you have a phase shifter on mode labeled 1 and not on mode 0, you don't do anything on the mode 0. We'll see the two cases. So if you apply the phase shifter on mode 1 on a qubit in state 0, then this phase shifter will have no effect, because no photons goes through it. So it's a phase shifter on mode 1, but the photon is on mode 0, so it has no effect. That's the first line. And the second way to, the second case is when you have a qubit state in a ket1 state, then you apply the phase shifter, but this time there is a photon in the mode 1 on which is applied the phase shifter. So it introduces a phase shift in front of this state. And in this case, we chose a phase shifter of pi, but this is something you can act on and you can calibrate. So you can make S gate and T gate just the same way, just by changing the phase that is applied, and then you get the Z gate. The Y gate is a bit more complicated, but it's not unachievable. You first start with a permutation, which you can identify as an X gate, and then you apply a phase shift onto each of the modes representing the qubit. So on the one mode, you apply a phase shifter with parameter pi over 2, which introduce the I component in the matrix, and on the other one, you put a phase shifter with minus pi over 2, which gives you the minus I in the matrix. The last one is the last simple one qubit gate I want to introduce you to is the H gate. And once again, it will be simple to implement. You start from a beam splitter and its general formulation, and choosing a parameter on which you can act instantly gives the matrix. And in this encoding, you have a one-to-one correspondence between the beam splitter's matrix and the Hadamard matrix. So there's something that is a bit swept under the rug. This matrix of the beam splitter will not have the same effect if you choose another encoding. So it's really, in this case, there's a direct correspondence with a dual mode encoding. So now I want to introduce you to control gates. And control gates are harder to implement with photons than the simple one qubit gate I presented to you. And the first thing, which is a limitation of photonic quantum computing, is that the C0 gates are non-deterministic. Even in a perfect quantum computer, you will have a chance that your C0 will fail. So that's something I want to put emphasis on. It has a low probability of, and it even has a low probability to succeed. You will be able to compensate that problem, but it's still something to be noted. And there are different ways to obtain a C0 in the dual mode encoding, and I will present two of the ways to you. So the first C0 I want to present was introduced by Wolf and al. In 2002. And it's a C0 featuring 4 modes for the 2 associated qubits. And you have to add on to the circuit 2 auxiliary modes. So you have dual way encodings for 2 qubits and 2 extra input modes. So on these modes, you will need to send no photons, and you will need to measure these modes if they have photons or not at the end of your circuit. So if there's a photon in one of your auxiliary modes at the end of the circuit, then you have to discard your computation because the C0 did not have the expected outcome. So that's where the problem lies, because if you have 2 C0s in a row, then you can have false success, because if you start with your C0, you can have your photons of the 2 qubits meet in a spatial mode in between, and you have no way to check because you can't measure your circuit in the middle of its computation. So that's one problem of this CNOT. And even if you measure at the end, maybe the photons will have gotten splitted. So you really have no way to check on this CNOT. But this CNOT has a good probability of success. Then there's another CNOT, which was introduced in the same year by CNIL, and it also uses auxiliary modes. Well, it's not really a CNOT, it's a CZ, but you can just make the CNOT from the CZ using 2 H gates. So that's why we talk about the CNOT, because we are comparing the CNOTs. This time, you can only see 4 modes, because on the 2 qubits used in the CNOT, you are only taking one of the two modes, of the 2 spatial modes in your dual rail, and it's the mode which is associated with the 1 qubit state, the Ket1 qubit state. This time, you input a photon on the auxiliary modes, and you need to find exactly 1 photon at the end. But this time, you do not have to check if it worked on the modes representing your qubits. You just have to check onto the auxiliary modes and not on the other ones. So this CNOT you can serialize, and you could put one after another, but it has a worse probability of success than Wolf's one. So I want to compare the two. You have Wolf and Al as a CNOT, which has a probability of success of 1 out of 9. And you have a CNIL CNOT, which has a probability success of 2 out of 27. So it's worse in terms of probability, but you can serialize it and chain it. That's I'm using both words a bit the same. So the other thing to note is they both use 2 extra modes, but CNIL's one, you have to generate photons into the extra modes as an input of your CNOT. You can, using this method, you can rebuild the Grover's algorithm using single qubit gates and probabilistic control gates. For instance, we can make this Grover circuit. And we will need to transform Toffoli gates using this decomposition. And each of the CNOTs in this Toffoli will have a probabilistic chance of failing. But during a post-selection, meaning only keeping the ones where the CNOT worked, because you can check if they worked, then you can get the expected results. Now I want to introduce you to polarization. I don't know if I've got a lot of time. I'll just check. Sorry? Try to keep it within 5 minutes. Okay. We can also use another property of light to encode qubits on, and that's the polarization. So the polarization is defined as the path described by the electric field associated with each photon. And from this electric field, you can define a vertical and horizontal position. For instance, here the vertical position is y, so a photon with the electric field in the y-x plane will have vertical polarization, and one that would be rotated would have a horizontal polarization. By leveraging polarization, one can reduce the number of spatial modes needed to, for instance, make a Grover circuit. But the gates will not be the same as the gates I presented to you. So really building a gate for specific encoding depends on the encoding. So the Z gate will not be the same, and the X gate might not be the same in different encodings. So here we have one other way to do it, and it's with polarization. And you will need to introduce new polarization-sensitive optical components, which I can name the wave plates and polarization rotator. It is not into the scope of this presentation, well, not presenting the action. So one type of polarization encoding could be this. So in the qubit state, you'd have Ket00 up to Ket11. And into the Fock state encoding, you'll have only two modes, but you will be using the tensor product between the spatial mode and the polarization mode. So having one photon in mode 1 with polarization H would give you Ket00 and so on. To conclude, I wanted to show you how quantum gates can be reconstructed in using linear optical components in the dual mode encoding. And I wanted to highlight how control gates are typically non-deterministic in some encoding. And I also wanted to show you how much there is a variety of different encodings into photonic. So if you want to read more on this, we have a paper on arXiv, which you can access.
Thank you. Any questions for the speaker?
Thank you for your presentation. I would like to ask a question about the probability of success of the CNOTs.
Okay.
Because you showed that there was like 2/27 or something. Yeah, 2/27 probability of success. But if I have a circuit of 1,000 CNOTs and I want all of them to be executed properly, then the probability of success would be 2/27 to the power 1,000, which is almost 0. So how do I run this circuit on photonics?
Well, you'd have to run it, I think, many times. I don't have any better solutions, and I don't think they have a lot of, I don't think the constructors have any better solutions with this encoding, once again, because the CNOTs in other encodings might be better. So there's a field of research of how to encode the qubits properly. This is one of the first one, and no one has found at least not to my knowledge, a better probability that can be chained than this one. So if you run your circuit a lot of time, you'll just have to filter out on your post-selection, because on this one, you can check if it worked by just checking the auxiliary modes.
Yeah, so you just exclude all the results that failed.
Yes.
But then if I have to run it, let's say 1,000,000 times or 1,000,000,000 times to get some significant amount of success, how long would that take?
Because they have to do this, they are trying to, each shot in a photonic is really, really cheap, and you can make a lot of ones on your circuits really fast, and that's how they are hoping to compensate. I don't have any better answer to.
Okay, thank you. Thank you very much.
Any other question? So to paraphrase, there is still open research in determining whether 2 to the power.
Sorry?
To paraphrase what you said, is still an open research question to go beyond 2 to the divided by 27, if I understand your answer.
Yes.
It's an open research question for.
So in this paper, introducing the CNIL CNOT, they give the whole process of how they build this CNOT, but they also said that they have no proof of optimality.
Right, so it's not right, okay, that's good.
Thanks for the nice talk. You mentioned that the each shot in photonic hardware is much cheaper because you can do it very fast. And is there any comparison of like take an example of Grover to successfully solve this problem? How much time it would take, and when you compare it with other platforms like neutral atom or trapped ions, they are extremely slow for each shot. So is there any such comparison?
I don't have it, no. But I think, no, I can't answer this, sorry.
And this probability is multiply, right? As the number of C-naughts in the circuit increases, the probability is multiplied.
Sorry, I didn't get the question.
As the number of C-naughts in the circuit increases, the probability is multiply, and you have to repeat it maybe trillions of times, even for...
Yeah, that's the problem I wanted to highlight.
Yeah, okay. Okay, thank you.
Any other question? Nope. I think we can thank all the speakers. And I think next step on the program is lunch. I think it's lunchtime or lunchtime.
No question.